Hi, folks. Everyone okay? Fine. So, hi, everyone. I'm really happy to be here. This is my first time in Ireland. So, for great news, great new event. So, it's really nice. I came from France yesterday. And just before beginning, I heard that somebody is coming from Argentina to attend the conference. I tried to figure who is coming? I don't know. Okay, if you recognize you, I've got a T-shirt for you because you won the long-distance challenge to attend to a conference. Really, congrats for that. So I'm really sorry to have been scheduled that late today because your brain is probably full of new things, new features, new brand things that you want to try when you're going back to work on Monday. But let me add a bit to the cheat load and talk a bit about WebAssembly and what WebAssembly is. So let's try to remind a little bit and go back in history. In 2001, there was a rebirth of JavaScript. We had new framework, new libraries like Prototype, Mutual, Scriptaculous. If you used that before you're old, and I'm old too, because I can remind it. In 2005, there's jQuery, a new abstraction library. You can use JavaScript in every browser with the same API, and it works the same in all browsers. Big revolution. And 2010, this is the arrival of Backbone, which is the beginning of a single-page application. And this is a big change because we start to build some application in the browser. And we do not develop websites anymore. I mean, you can still develop websites, which are pages that you consult, but you can still, you can now have real application that you want to use directly in your browser. 2012, this is Angular. 2015, Virtual DOM, React, Vue.js, and so on. 2018, the progressive web apps, where you can run with web technologies application natively in your browser and in your mobile device without notice that this is a web technology behind it. And now, how is your RAM? Because mine with 8 GB is sometimes not enough to handle all my web applications. So we've got a big problem about it because we are now developing apps. We are not developing websites anymore. So we have to handle the common patterns to develop apps. And we need a new technology to handle it because we all want a better internet. So we all need a new virtual machine to run new code and new stuff directly inside our browser. But what do we need? We need a secure environment because we want to run application in our browsers, but in a secure way. We need a faster execution because JavaScript is sometimes too slow to handle all the use cases that we have. And we need to share domain logics. Because if I have some data models on my server, on my backend, or in dedicated application, I don't want to redevelop it to handle it in my web browser. I want to write once and run everywhere. And this is exactly what WebAssembly stands for. This is a big promise. So how to use it? Not that easy. Because this is an assembly format. So it's a binary format, and you have to write it close to a CPU machine instruction. So you have to write it in a binary form to run it. Every day in my work, I want to write that. I mean, it's a language. Fortunately, WebAssembly comes with another format, which is the WebAssembly text format. And I can write my code like that. More understandable, no? No? No, I don't want to do that anymore. I need something more useful. I need something more high level. I need to compile for the web. I need to write my application with a big language, a new high level language, modern language, and I want to compile it to the web. So I need now to pass my code through a compiler, like LLVM, to output a binary format that is able to run into the web. So if I want to write it with Rust, let's say, because it's a pretty cool language, I have to declare a function. I will call the native alert method directly in it. I will pass an argument, and I will format that argument using the format macro available in Rust. And if I want to use it in my JavaScript code, I just have to call my function into my wasm module, and I can't call directly my function. I call the alert method directly from my module. OK. The fact is, in WebAssembly, we've got 4 static types. It is a statically typed language. We have 4 static types. We have 2 integers and 2 floats. And that's all. It's problematic because I need more. I need more than numbers. I need strings. And strings are often complicated. That can be a really, really shitted format. And I need to use it to handle it. So it's complicated right now. But we've got a solution. Because a number can be a memory pointer. So I can use my number to point to a memory cell and access the memory cell directly into my wasm module. Let me introduce you to linear memory. This is a concept. You've got a virtual memory instantiated into your JavaScript module, and you can access it through your JavaScript code or through your wasm code, and you can share your part of elements, your variables, from one module to another. So if I want to do that, I have to instantiate the new memory module into my browser. I will initialize it, and I will construct a shared memory, which is an array of unsigned integer. Why? Because this is the only way in JavaScript to handle binary formats. So I will initialize it with the array buffer contained in my linear memory. I will initialize my pointer. Then I want to store in my shared memory, my linear memory, the string hello world. So I will call the for each function on my string, or probably more on the binary form of my string. And for each character in my binary formatted string, I will store the char code into my shared memory at the given position of the pointer. And boom, I've got a virtual memory, the linear memory. And I could use it in my JavaScript, because I could write my data in my linear memory. And I can use it in my wasm module, because it's just here. My module can read this part of memory. Somebody want a pen skiller? Because me, I don't want to do that every day. I don't want to deal with the shared memory in my day-to-day work. I need a high-level tool to do that for me. I don't want to handle the memory by myself. Please. So what about instantiating the module? Because I don't have any script type wasm or WebAssembly module ready right now. We have the script type JavaScript, and that's all. So I need to fetch my module, which is binary format. I will get the response in a premise. It gives me an array buffer, which is the binary representation in JavaScript of the binary format. So I will instantiate my WebAssembly module using this binary format. So I can access the module, and more specifically, I can access the module instance exports, which contains the methods available in my modules, and I can call it directly with the parameters that I want to use. And not that easy. And what about the execution timeline? I mean, I will load my WebAssembly module. So first I fetch it. Then I load it into my JavaScript code, and the JavaScript code will compile it twice. First one, because he has to read the format to understand and to build an AST of the wasm module, and the second time to improve the performances. Then we can instantiate the module, and then we can access the function in it. Well, so we need a packer. We need something to do that for us, because I don't want to fetch my module manually and instantiate it and control the compiling time. No way. So what do we really need? We need a language with static types, which is ready to compile to the web. We need really good memory management, because we've got memory to handle and to manage. We need bindings to JavaScript, because I want to exchange data between my JavaScript module and my WebAssembly module. And we need a packing toolchain, because I don't want to do it by myself. What we do not need is a new virtual machine, because we already have one. We've got the JavaScript virtual machine, and it's a pretty good one. It runs in every browser, it runs really well, and having the same virtual machine that is able to run both JavaScript code and WebAssembly code allow you to have really, really fast operations when you exchange things and data between the two kinds of modules. So we do not need a real new virtual machine. We already have one. We need to exploit it. So what about the security in it? Because we want to secure the environment. The security model of WebAssembly is pretty good. It's sandboxed. Each WebAssembly module runs in its own environment, its own level of execution. And you can't access any kind of data in it if you are not allowed to do it. It's a black box. There is the deterministic execution thanks to the static types. So it's pretty efficient. We have control flow integrity. We have a protected code stack in linear memory, so no more buffer overflow. Pretty good. And we have the embedding security policies of the environment. So in your browsers, this is the security policies of your browser. And with wasm, which is the server version of WebAssembly, we've got the POSIX security policies. So it's really strong. So hands on. How to do it? Let's focus on Rust. So remember this one? OK. So let's continue. Why Rust? Because C++ is a pretty good language, but I only have one brain, and I don't want to split my brain to handle the memory on one side and handle my code on the other side. I need more better languages than the C++. There is no data race in Rust by design, so it's pretty cool. You can run it even in multiple threads, and you don't have any kind of data race because the design of the language forbids itself. You have static types, which is mandatory for WebAssembly. We got pretty good iterators, an excellent memory management, and an awesome community, a big toolchain with Cargo, and Cargo is the package manager of Rust. And Cargo is built by the team which previously built Bundler, which is a package manager in Ruby, where they really know their job and they do it really well. And there is much, much more, because we have was.wasm. Was.wasm is a library that allows you to bind native JavaScript function directly into your WASM module. So you can use JavaScript and method directly into your modules. It's a high-level library, pretty easy to use. It exposes all the web system. You've got access to the DOM, window, document, fetch, canvas, audio API, and so on. You have all the JS systems, so all the JS types, the boxing, which is a pattern in the JavaScript virtual machine that declares the type of the variables that you want to pass, because JavaScript is not typed, so you have to declare the type of the variables that you pass at some point. You've got access to promise. You've got access to TypeScript bindings automatically generated by the WASM module and the Rust module WASM bingen. So it's really useful. When you want to use it, I've got my greet method, the same like before. I first initialize my WASM bingen module with its primitives. And I want to access the native alert method in my browser from my WASM module. So I just have to declare it, because Rust have to be aware of the existence of the method. So I just declare the alert method, and I say, because it is embedded in the C module, that is the command module, that you got access of the alert method, it's available. You can run it now, and that's so on. It's available for the native API, but it's also available for your own modules. If I want to write a module which bridges some JavaScript logics to my WASM code, I can do the same thing with a module. I declare my module, and I can declare the function exposed inside my module and access it directly into my Rust code. And it works. So I can update some state and passing some JavaScript values, and it will update the state directly into the JavaScript machine. More, we've got WASM pack, which is a packer dedicated to WASM for the Rust environment. So it simply took your Rust code. It relies on Cargo, the build tool of Rust, to build some things and generate the code that you want to use into your modules directly. It means that you just have to install it, just have to call it with a build target and eventually release format, optionally in release format, into your code. And what we'll have at the end, something like that. I've got my bridge, which is my API bridge from my application, the cargo toml, which is the same thing that the package JSON file. And I've got my package. And in my package, I've got the WASM binary module, the code, JavaScript, the JavaScript module that is responsible to load the WASM module for yourself, so you don't have to do it manually by hand. You got TypeScript declaration, and you also have the JSON package JSON file. So your package is ready to be published directly onto NPM with just one single command. Trust me, we didn't have it 1 year ago. It was way more complicated. So, a state of WASM, how to use it in everyday. Because I'm a guy that works on security concerns and cryptography stuff and so on. I wanted to make a demo where we can find if WebAssembly is really fast and faster than JavaScript. So I wanted to build a kind of blockchain. So what is blockchain? A blockchain is a collection of records. The blockchain is composed of an array of nodes, and each node contains an idea, which is a checksum, a parent, which is the parent ID, so the checksum of the previous node, because it's a blockchain, it's a chain of blocks, so you have to maintain the chain at some point. There is a nonce, which is a random number, and an array of records. And each record contains an ID, a checksum, and a payload with whatever you want in it. So if I want to mine the blockchain in the term of the Nakamoto consensus, which is used in many crypto money, like the Bitcoin, I will first make a loop in JavaScript. I will generate a nonce, so a random number, a long random number, and I will store a node ID. And the node ID is the checksum of the nonce, sorry, the parent node, so the previous node in the chain, the previous checksum of the previous node, the nonce, and stringified representation of the records of the node. I will generate the checksum. I will store the checksum in my node ID. Then I will split my checksum and just compare the start of the checksum. I want to find an arbitrary number of leading zeros. It can be 2, 3, 4, 5, 10, whatever you want. If my checksum starts with the correct number of zeros, I break my loop, and I go outside of my loop. Otherwise, I shuffle the records, and I start it again, unless I could find a nonce and a composition of my records that could generate the correct nonce, the correct checksum that start with the correct number of leading zeros. Okay? Okay, if I want to do that in JavaScript, this is something like that. If I want to do it in Rust, this is it. A loop, I mine my node, and I break the loop when I've got the correct number of zeros. Why? Because Rust is statically typed, so I have to declare my structures, and I can extend my structure and declare some method in it, so a mine method, in which I will initialize random number generator. I will shuffle the record, generate the nonce, generate the ID, and test the checksum to find if it starts with the correct number of zeros. And that's all. We see it in action? OK, so here's demo time. Woohoo! We've got 3 blocks. Each block contains 1,000 of records. I display only the 10 first, but trust me, there is 1,000 of records in each node. They are composed of some random data, like an address, an email address, a phone number, and so on. A random ID, which is a checksum too. And my blocks are chained because my second block uses the parent ID just here. So the parent ID is 0 because this block is 0. This parent ID is 1 because this block is 1, and so on. OK? So I will first try to generate a nonce in my first block to get the correct leading number of zeros in my idea. Then I will mine the second block, then I will mine the third, and so on. So I will run it first with JavaScript. Go. It is rendered. The render function is located in a request animation frame, so it doesn't have any impact of the performance of the loop and the render. I want 2 leading zeros, and I've got my 2 leading zeros each time. We can see that the chain is maintained because this is the same parent ID for each block each time, and we made it in 60 seconds, so something like 39 milliseconds per run. We'll do the same with my Rust code compiled to WebAssembly. Just, I will reset the state at the start point, and I will mine with the Rust code, but I won't update the interface in real time like in JavaScript because I was too lazy to implement the backend first function to render it in real time. But trust me, it doesn't have any impact. So in WasM, it reset. It is performed in the background. This is why the state is on, and so on. So 9 milliseconds per run. Way far better. This is really fast. And this is secured because it is executed in a dedicated sandbox environment. And the JavaScript can't access it if you won't allow your JavaScript to access the data inside the WasM module. So it's really, really efficient. So what's under the hood? Just right now, there is a Fantastic Four. Each major browser and latest release support WebAssembly in production right now. You can use it right now. And this is the case in some NPM modules. It's an open standard with a wide adoption. We could compile. It's fast. It's lightweight. And we've got the linear memory with the typed everything. But it's hidden behind the WasM binary library. So it's usable. What's coming soon is the multi-threading. Because we can do multi-threading right now in the Rust application, but you have to run your WasM module in a web worker, and you have to instantiate it manually, and you lose some native browser primitives in your web worker. So it's a bit tricky right now, but there is a proposal of multi-threading directly available in WasM, and WasM will pop some new web workers to do some multi-threading in the web browser. So it's pretty ready to ship. A better streaming compilation with a tiered compiler, so no more twice compilation. It will run your WasM module at the same time the WasM module is served to the web browser, so way faster. We will have module exchange and access to the garbage collector, which is not the case right now, so you have to have some workaround to access some spaces of memory in your WasM code. We have to handle it, but it will be solved soon. We've got portability, a big runtime and many runtimes access for IoT. It's pretty cool. We've got the WASI, which is WebAssembly on server in the POSIX environment. So this is something like Docker, but in a lightweight form and probably more efficient. So it's really, really fun. And thanks to interface types, we now have some binding modules available in any language, which means I can write my code in some language, compile it to WebAssembly, and call my WebAssembly module from anywhere. JavaScript, Python, Ruby, PHP, whatever you want. You can have already some bindings available to load your WASM module in any language you want. So you have to know the web. We've got HTML and DOM to declare our interfaces. We've got CSS to make some styling on our layout. We've got JavaScript, more and more dedicated to UE threads and only UE threads. And we will have, and you already have, WASM to handle big computation in background processes. Thank you very much. I'm Mads. I'm a tech evangelist. I'm working at Always Data. We're a PaaS provider, and we keep an eye on WebAssembly, both to have it available for our customers and to power our CLI and our own libraries to access to our platform, because it's really, really useful to do that this way. If you've got any question, I will be here, and I hang out at the party, so let's come and chat over beer, and thank you for everything.